Hi, welcome to Lab 3 where we examine how we can use an object's trajectory to calculate the mass of another object. This lab uses Newton's second law to calculate the mass of a black hole by examining its trajectory and the time that the object is at each location. Gravity is the main attractive force between any two objects with mass, and this is the main force that we use in this lab. The net force is made up of perpendicular and parallel components of force. What does it mean for a force to have a parallel and perpendicular component? Net force can be expressed as perpendicular component plus the parallel component of force. The parallel component corresponds to the object speeding up and slowing down, and it is in the tangential direction of the object's motion, meaning it's in the direction of an object's motion. In this model, we can see that the object will have the greatest parallel component when it's closest to that object, because it will have the largest net force. The perpendicular component of net force corresponds to the object changing directions, and the perpendicular component always points to the center of the kissing circle. Here is the computer model that we created. In this model, the orange arrow corresponds to the net force, the pink arrow corresponds to the perpendicular component of force, and the blue arrow corresponds to the parallel component of force. As you can see, the blue arrow was largest when it was closest to the black hole and smallest when it was further from the black hole. Now let's step through the code. First, we identify the gravitational constant g and set the mass of the star equal to 2 times 10 to the 30th kilograms. We set delta t equal to 1 day in seconds and set the first observation point as 0 seconds. We then started a while loop where we were able to calculate velocity by examining the change of position in the x and y direction. We then set up a calculation while loop. In this loop, we started by creating a final and initial velocity vector from our calculated x and y velocities in the last while loop. We then found momentum by multiplying mass times velocity, which is part of the momentum principle. We then found the change in velocity and the change in momentum by subtracting the final velocity from the initial velocity and the final momentum from the initial momentum. We then set dB dt equal to the change in momentum divided by the change in time. We said net force is equal to dB dt per the momentum principle. We then were able to calculate the parallel component of the force by finding a unit vector, finding the change in magnitude of momentum, and multiplying this times the unit vector. We then set Fnet equal parallel equal to the change in momentum parallel. And then since we know that net force is equal to the parallel component of force plus the perpendicular component force, we can rewrite this as net force minus the parallel component of force equals the perpendicular components of force in order to find Fnet perpendicular and dB dt perpendicular. To calculate the mass of the black hole, we rearranged the gravitational formula to isolate the mass of the black hole. The first thing that we did was take the magnitude of the star's position calculated in the previous while loop and squared this. We then said that the star's position squared times the magnitude of net force divided by the star's mass times gravity is equal to the mass of the black hole. We then printed the time that the mass was calculated and the mass of the black hole. While there were some calculations, we found that the average mass of the black hole was 1.55 times 10 to the 34th kilograms. We have fluctuations in the mass throughout the time that the code runs because we are not using exact numbers for each calculation, so we get slight variations, as seen in the graph above. One of the questions we were asked are how is net force and its parallel and perpendicular components different from the rate of change of momentum in its parallel and perpendicular components. Per the momentum principle, net force is equal to the rate of change of momentum. They will have the same value in the same direction. However, they are very different concepts. The rate of change of momentum is found by studying the motion of the object as it moves along a trajectory, while the net force is found by summing the forces of an object. If we know one of these quantities, we can use the momentum principle to update the other. Essentially, momentum change is caused by the net force. If we were to switch this black hole for another with a different mass, what would happen? For this question, we can assume that the black hole is at the same location and the star moves along the same path. If the star is moving along the same trajectory and the black hole is at the same location, then the black hole must have the same mass in order to have the same trajectory. That is because if we change the mass of the object, then the gravitational force on the star and on the black hole will be different, and this would result in a change of scale in trajectory. For example, if the mass of a black hole were to increase, the star would be pulled closer and the trajectory would shrink. In conclusion, through the manipulation of Newton's second law and the gravitational formula, we can determine an unknown mass by looking at the path of an object and its interactions with the other mass. Thank you for watching.